Yeah, hi everybody. My name is Evgeny. I'm from the RWTH University in Aachen in Germany, and I'm very happy to present our recent research on neural language models and few-shot learning for systematic requirements processing in MDSE today. So let me start with basically a short overview over what I'm going to talk about today. This project arises in the scope of a large cooperation between us and an automotive manufacturer in Germany. And such automotive manufacturers, they have to deal with thousands and tens of thousands of requirements in their production. So it's clear that no single person can memorize all these requirements, and that we need some kind of automated processing techniques, for example, for consistency checking on these requirements, to compare requirements to make sure that no requirements are double, and so on. So the idea here is, and this is not a new idea, to introduce some kind of formal notation for requirements. So in our case, we would like to introduce a DSL to formalize requirements, which are at this point mostly formulated as informal text by the requirements engineers. And the idea which is new here in this work is basically to use machine learning in order to translate the old informal requirements to this new formal notation. So the problem with machine learning, or the challenge when using machine learning, is of course that we need lots of training data to come up with a model which is suited to solve such a complex task, such as translating requirements from informal language to a formal notation. So the solution we want to present here, or which we want to evaluate here, is to use a large pre-trained models with very high capacity, which have been pre-trained on large amounts of data, to basically fine-tune them to this complex task with relatively few examples. And in particular, we want to use an approach which is called few-shot learning here, which has been very popular in recent years. The idea behind few-shot learning is that instead of training models for a very specific task, we train models for basically for accepting task descriptions and then solving these tasks on demand, so to say. And this approach has been shown to work very well with large NLP models, such as the GPT, in recent years, because these models, they are very general. They are trained to basically take an input text sequence and to output a continuation of this sequence. So the idea is, in this case, that we would give some examples of how the translation should look like for our purpose, and would hope that the output of such a model would be the correct translation for a new example. And usually it's enough to give only a few examples, like 3 or 5, to make the model understand what it's supposed to do. It's basically very similar how we humans learn new tasks. So also, if I wanted to tell you how to translate a requirement from informal to formal notation, I don't need to give you thousands of examples, but maybe 2 or 3. And basically, this is very similar how these models work. So this is, of course, computationally very cheap. I just give the model several examples, and it's ready to go, hopefully. So here is basically an example how we do this. So we take a large NLP model, and as an input, we provided several. Sorry, I just skipped a slide. Excellent. So in order to evaluate this, we looked at a publicly available automotive requirement data set, looked how it's structured, what kinds of requirements we have in these requirements, like how they're, what kinds of formulations they use, and how we can improve them by using DSLs. And we came up with basically 3 very simple language constructs. The first one being the trigger action requirements. So in trigger action, or in cyber-physical systems in automotive, we often have to deal with requirements which are formulated like, if there is a trigger, for example, from a sensor, then something needs to happen. So for example, if I push the pedal, then the car needs to accelerate. and stuff like this. A second rule for us is the introduction of modal verbs. So we realize that many requirements lack modal verbs, and then it's ambiguous whether this is a requirement or a pure description of something which is already there. So for example, if I say that the car drives 100 kilometers per hour, it does not sound like a requirement, but sometimes it is. So it should be formulated like the car must be able to drive 100 kilometers per hour. And the third thing is expressions. So often we need to compare things to each other in requirements, and this can be done in informal language in lots of ways, which are also difficult to analyze. So we want to introduce here keywords to express this. And having come up with such a simple DSL, we now would have to translate some requirements manually in order to be able to teach the neural language model how to translate them in the future. And this is how we do it. So basically, in the red boxes, you see the translation pairs where the input is followed by an informal requirement, and the DSL part is, so to say, how this should look like in our model. So for example, in the upper red box, we have an input requirement starting with an if, and here we introduce a specific if keyword in capital letters, and then this then keyword in the middle of the sentence in order to separate the trigger from the action, so to say. So we have two examples given here, but they're all part of one of the same input string. And the last part of the input is this green box, and this is basically the task we want to solve here. So it's the requirement to be translated. So here we only give the input, but not the translation. And then we hope that the model would come up with a correct translation. So for our evaluation, we use the GPT J6B model. It's a 6 billion parameter model, which is an open source model, which is very similar to the corresponding GPT-3 model with 6 billion parameters. It's a very high performing model, but not the largest which is out there today. And in order to understand how many examples we need to provide to the models, we tried to teach the translations with 1, 4, and 6 parameters for each of the 3 translation rules or DSL rules. And we introduced a classification system for the translation quality from 1 to 6, where class 1 translations are perfect translations, and class 6 translations are basically rubbish. And we can see, for example, in the first 3 lines for the if-then, for the trigger action requirements, that when showing the model 1 example, we only have 2 class 1 translations, but when increasing the example set up to 6 examples, we already come up with 6 class 1 translations out of 11. So basically, the model learns really, really fast here, which is very promising. So meaning that with really few examples, we can achieve very good results here. So let me give you some examples how these translations worked out. So for example, at the very top, we see a requirement which was formulated a bit ambiguously in the way the frame rate of the camera is 60 Hertz. So basically, this is not a real requirement, but it should be one. So in this case, the translation correctly translated to the frame rate of the camera must be 60 Hertz. Similarly, we have this for the other 2 examples. So for example, the luminous intensity of the daytime running light must be lower than 400 candela. And here we introduced basically the comparison keyword less than on the right-hand side. And the third example is that the hazard warning, as long as the warning light switch is released, all the direction indicators flash electronically. And here you can see that we have this if and then keywords introduced at the right places so that we can separate the trigger from the action very easily if, for example, analyzing the requirements in an automated way. We have a technical report online, which contains all the experiments and translations. So if you like, you can look all the examples up there, and also all the training sets. So I'm already arriving at my conclusion, which is basically that high-capacity language models are capable of learning DSL translation tasks for requirements with really a few examples, which also enables us to create very tailored DSLs for different requirements domains, for example, like automotive, and introduce them in a cheap way without having to train requirement engineers and to spend a lot of time to translate all the requirements manually. However, there are still problems with that. So some of the requirements we were not able to translate using this approach. So sometimes it's still a little bit difficult. But our hope is that since the machine learning domain in this area develops very quickly, that with even larger models, the translation quality will become better. Thanks a lot for your attention.
Yeah, to directly run frequent learning, did you apply any pre-processing to the input? Did you just give the input as it is to the model?
Yes. So basically, the only thing we did was to translate the examples we wanted. Basically to give us example manually, but that's it. So no further pre-processing. Oh. Yeah, basically you need to, if you have a text sequence, you need to tokenize it.
Hi, thanks for the interesting talk. So generally, my question is a little bit high level, right? So generally, language models, especially like the ones you showed with transformers, they are notoriously unskilled with basic math, right? Numerical stuff.
That's correct.
And requirements, I'm guessing if you want to express complex requirements are going to have some constraints, some form of expressions that are very mathematical in nature. So if I were to use a system like this, I would be quite concerned about generating requirements that are...
That's exactly what I said. There are still some things which are not translated correctly. That's exactly what I'm referring to. So for example, for such a model, less than and greater than is often the same thing, because statistically it's the same thing. Interestingly, in some cases we realized that with more examples, the model somehow learned to use, for example, greater than instead of less than after some examples, which was interesting. But this is exactly the problem. But still, also the idea here is if I'm trying to introduce a new DSL, it would still be helpful for you, for example, as an requirement engineer, say, okay, I have this translation, it might not be perfect, but as an engineer, you just maybe need to switch the less than to greater than, but you already get the syntax basically for free.
We are facing similar problems with the upcoming research. Probably we should talk.
Yeah.
I have two related questions. One is that the window that you're allowed for the translations to be 4K characters. So the input that you can use for training and for the actual task is relatively short. And requirements tend to be notoriously long. So how much can you actually do in practice, and how many training examples do you need? When these were clearly designed to fit the slides, but how does it look in practice?
So this is a slide I skipped. I'm not sure if I still have it here. So basically one thing we do to solve this problem a little bit is that we train a model, or we do sequential processing. So for each rule, we have a separate training set. So I first, for example, do the if-then translation. Then with this translate model, I do the next syntactic element and so on. So this already helps me to save a little bit of this window. But of course, if you have very, very long requirements, it will become difficult.
Do you have some, does the model know how confident it is about the translations? Can you give some, does it output some kind of confidence level?
Some kind of
confidence
level? Not at this point, no. But this would be a very interesting way for future work.
So GPT-3 has been shown to develop good programs from textual input, but when it goes wrong, it goes completely wrong. Did you experience that at all, and how do you cope with that?
So there is the concept of few-shot complexity, and the few-shot complexity in basically outputting complete programs from textual input is very high, I would say. Here, the few-shot complexity is relatively low because the DSL we introduced is very similar to the informal input base. So basically, instead of creating something completely different, we rather introduce keywords at specific places. So being said that the few-shot complexity is relatively low, we did not have examples which were completely out of scope. So there were some kind of misunderstandings by the model, and here the model confused something, but there was nothing completely wrong.
My question is, it's low level and it's more because I'm curious. I was wondering, when you're running the executions, are you playing with the hyperparameters such as the temperature?
We did that too, but there are not too many hyperparameters to tune there.
The
Temperature,
for instance, has a huge impact on the results. I think I was also wondering, how many times do you run the queries? Because you execute the query several times and then you get different results. Or do you execute it only once? Do you execute it multiple times and then you analyze the frequency of some of the works and then you pick one solution? Or how do you?
So basically, when all the hyperparameters are fixed, the output would be the same for the same input. So it would not really change.
Oh, because of this model, because I have played with GPT-3, so I haven't played with this model that you're using here, but with GPT-3, if keeping the same shots and same task description, I run it so different executions give different results.
So we have the iPipe notebooks there to execute this, and basically the outputs were, I don't know with the greater, more bigger models, or if you're have a very high temperature, maybe you would introduce a random factor, but basically here.
No, as I said, I was using GPT-3, so I was querying OpenAI. So I don't know what's happening behind the scenes, but that might be.
So here it was quite reproducible.
Thank you.
Thank you very much.
Thank you.
Time to close the session, so thank you very much for all the speakers and conclude the discussion.